Good morning and welcome to Introduction to GPR for Concrete. My name is Huw James. I am the National GPR Sales Manager for PCTE. My background is that I am a surveyor who has worked for 20 plus years in the survey industry as both in sales and as a on-site surveyor across construction, mining and service locating. I'm also a bit of a self-confessed survey nerd. The object of today is to give you a very brief introduction to GPR for scene setting for later on in the day. So this will be a very much an introduction for someone who has never used a GPR before. So the first question we always have to ask is, what is ground penetrating radar? Ground penetrating radar, which we will call a GPR from this point onwards, is a non-destructive geophysical survey that uses radar pulses to create images in the subsurface. It works by sending electromagnetic waves into the ground, analyzing the reflected signals of buried objects or features. So in brief, our ground penetrating radar, as it passes over, is going to send an electromagnetic pulse into the ground. That pulse is then measured, and any changes in the reflection will be shown in our screen. So what we see is not the object, but the reflection of the object, the reflection of the signal of the object. So what does that mean when it comes to what will my GPR scan look like? So there are 4 ways that the ProSec units can present their data. The first one I'm going to talk about is our image on our left, which is the grayscale image, which is a B scan. Okay, a B scan is a atypical result that you would get from most GPRs. In this case, it sends down the signal, and when it hits the object, we get a clear change in signal, and that creates the objects that we can see on screen. Now, these can either be arcs, curves, straight lines, or just changes in the wave pattern. What we can then use that for is, if we take the very top of the arc, we can work out the center of our object. Now, this can seem a bit overfacing for a novice user. So we like to combine that at first with our migrated view, which is down there on our right. On the right-hand side at the bottom is our migrated view of the same image. Now, although it collapses the Rio to give us hotspots, which are clearer to see and understand, because now we're seeing a circle, so it's giving us more of a Rio shape, a rebar shape, or a longer, more elongated shape for the bottom of our slab. It's not as accurate. With our B scan, we can detect the exact top. However, that exact top, which was marked in that first scan, obviously, as you can see in your scan at the bottom, is no longer shown as the center of our migrated. So even though it is more visually relatable, we do sacrifice some of our accuracy. Other ways you can see data with a GPR scan come by doing what we call a grid scan. A grid scan is where you have a set size and shape area that is broken down into grid lines, and we scan each of these grids in a methodical way. Once they have been scanned in that methodical way, the ProSec software can stitch these together to give us a total holistic view. Okay, so on our left here, we have our first view that we provide, which is a time-size top-down view. In this view, we can select, using the slider, the thickness of the piece of concrete we wish to investigate, and how deep below the surface we want to go. Once we have done that, it's going to remove any data that we have that is outside of that area, which can give us a very strong sense of where our Rio is running through these very clear hotspot lines. The disadvantage of doing this is obviously it is more time consuming on site for than doing individual line scans, just running the machine across and looking at the B scan. However, again, for a starter or a novice, it is highly useful for being able to manage and understand your data. And finally, we have one of the great differences of the ProSec unit, and that is our rotatable 3D image, which has been rendered and created via AI. So by taking the hotspots found in our grid, we can create this model of our rebar, which will give us that strong indication of how they are running with each other and a understandable relationship to each other. Okay, unfortunately, at present, we can only visualize and view this on the tablet. We cannot export this 3D model. So, what can a GPR tell you and what can't it tell you? First things we must get clear is one of the great misunderstandings of GPR is no GPR cannot tell you the size of a piece of rebar. Okay, as you can see in our B scan, what it is actually seeing is just the top and not the exact sides. So without those exact sides, we cannot see the size. Okay, this means that we cannot tell you the size of the rebar, but we can tell you the spacing, the location of the spacing and the location of the center of the rebar, the depth of the rebar, but we cannot then tell you the grade. What I mean by the grade is how much has this deteriorated in the concrete. So what may have been originally a 16 mils straight piece of Rio may have come under so much pressure over time that it is worn down and misshapen to become an oval shape that is maybe 14 millimeters long, wide. So that again is not something we can confirm using the GPR. Okay, so a GPR is not just obviously about rebar. We can locate post-tension cable. Okay, and we can also show you how to recognize the difference between post-tension cable and rebar. One will be a more narrow, wider arc that goes up and down as it travels across the slab, whereas a rebar will have a tendency to be a more tightly fitted arc that goes at the same height across. Once the GPR has traveled through a piece of concrete and got to the air on the outside, we will get a change of reading again. So this allows us to give us our concrete thickness. Now this is referred to in our industry as the back wall, which not only includes the sides, but actually the base of your slab. So we can tell you the thickness of the slab. We can show you where there are going to be hidden features such as footings. We can tell you where dowels are going to be positioned and where defects are. It will do this by once it interacts with this feature in a different way, we will get a change of signal shown in our B scan. Okay, what it will not tell you is the strength of your concrete. Okay, yes, we'll be able to tell you that there is a defect there, but we wouldn't be able to tell you how much that defect is affecting the concrete structure. So the other thing is that even though we are talking a lot about slabs at first, it's not just for slabs. We can use it vertically on walls, we can use it on columns, so you can scan one side of a column and actually go all the way through to one side at the other side. We can do beams, we can do drop panels, and we can do building cores. So pretty much any item that is square and has a flat surface and the machine can be run across in a building that is made from concrete, we can scan with our GPR. So what I want to quickly do now is run through our ProSec range of units. We break those down into two main sections. There's the handheld range, which generally are used for indoor slabs, walls, and other such item and stuff indoors. They come in three sizes. We have our workhorse unit, which we call the GP8000. This is a very strong unit with a lot of muscle. It covers a huge range of frequencies, and we believe it is by quite a way, personally, the best unit on the market as an all-rounder. We have two versions. We have a Pro or a Lite. A Pro unit will give you the ability to do exports and reporting, but also our augmented reality. Okay, whereas our Lite version is more of a push and mark unit. So it really depends on the sort of workload you're looking to do. The GP8800 is our small handheld unit at 65 centimeters square. The unit can be held in the palm of your hand. It also has a detachable battery, allowing you to pass it underneath low-hanging pipes, and gives you that really close access for difficult to reach places. And finally, our second specialized unit is the GP8100. This is for covering larger areas. So this has 6 parallel facing aerials. These aerials are collecting the same amount of data, equally spaced the same aerials as in the GP8000, okay, except there are 6 that are equally spaced across the unit. This means that the one single push will cover 6 times the amount of space that a normal GP8000. This is very good for hallways, small slabs, and other mid-size sort of areas. Okay. If you have a bigger slab, we would recommend you move on to one of our push GPRs. Okay, so we have 2 at this present moment in time. The GS8000, which is our standard push behind single channel unit, which you can push it along and it will cover a slab. It will react in pretty much have the same behavioral nature of a GP8000, except it has the ability to go to a much deeper depth and obviously cover a much larger area of time in a shorter period. This also has, when combined with its Pro functionality, the ability to be attached directly to a GNSS. This GNSS can give you a real-time location of a surface as long as you can see the sky. Should you be looking for an indoor machine that can do that, it is possible to have the unit measure using a total station. But if that is something you would like to discuss, please reach out to either myself or to have a chat with Will or Joel whilst you're there today, and they'll be able to fill you in on some of the details. The final machine I want to talk about is our GS9000. This is our large-scale GPR array. This is perfect for large slabs, wharfs, and bridges. It has a massive 50 aerials, which are cross-polarized, which allows it to see in both directions. So as we travel along our bridge, we will get a scan going parallel with the unit and perpendicular with the unit. These will then be meshed together over the 50 channels, so give us a complete reading over a swath of 900 millimeters wide. And again, this unit has its own GNSS unit included, so we can actually see where we are at all times. When you are ready to move beyond just marking on a slab, or you want to use one of our GS units, we highly recommend you also look at one of our 2 pieces of GPR software. One thing that I do like about personally about ProSec, a single license will get you access to both of these softwares. Okay, so you don't have to make a choice. You can get both for the same price. Okay, so GPR Slice is the classical GPR software that ProSec have had for many years. It has a very good reputation in the market and is extremely good. However, can be limited on size of data packets. Next, we have GPR Insights. So GPR Insights has been built as an addition and a replacement for GPR Slice. It has all the same power and capabilities as Slice. However, it has also been designed to take in the data from the GS9000 and other such machines, as well as the GS, so you can process large quantities of data very quickly. This is a cloud storage unit, so you don't have to worry about how you're going to have the computer time to process such large amounts of data. This then combined with the units gives you the ability to create high quality reports, images, and data packets that you can send to your clients. So that's all I'm going to talk to you guys about this morning. I want to say thank you for your time, and please enjoy the rest of the presentations. I hope you find them informative and that this brief introduction has given you a good idea of where we're looking to market and place the GPR in the workspace. So I would like to say once again, thank you for your time.
Cool. Thank you everyone for listening to Huw, and also a big thank you to Huw for his presentation. My name is Joel Shinoy, and I'm from the New South Wales office. I'm a materials engineer and I work as a technical sales engineer, looking after New South Wales and the ACT. I've been with PCT for about 3 years and a few months, and I look after the GPR laboratory and the NDT range. Cool. So with this presentation, I just really wanted to expand on a few pointers made by Huw with his presentation. Basically with ground penetrating radar, the frequency range you would normally get would be 0.2 to 4 gigahertz, which covers both low and high frequency ranges. You normally get about 700 mils of depth, but realistically you would get around 500, 600 mils, because that could depend on a lot of factors. Factors including whether you have a dense reinforcement, whether the concrete is wet or moist, and whether there are also any other embedded objects that could affect the penetration depth. The main applications for using GPR would be you would normally want to locate multiple layers of rebar before drilling or cutting or coring. Previously, with from what you've heard with the cover meter, you're limited to just locating at the first layer of rebar, but with GPR you can locate multiple layers. It's also mainly used to investigate on unknown structures. If you just want to look for any embedded objects on the slab, GPR you would be able to find both metallic and non-metallic targets. You will also be able to find slab thickness measurements. So if you've got a suspended slab, the GPR will be able to penetrate all the way down and find out the air interface, and with that you'll be able to get the slab thickness. Also for quality assessment and uniformity. Key features with GPR. So with the image on the top left, the grayscale image, this is what we call a non-migrated view. It's in grayscale. The image below that, this is what we call a migrated view. And then with the Pro version of the GP8000 and with the rest of our radars, you will be able to get an area scan like view and also a 3D portrayal of your area scan.
1 second, Joel. We have a question from the room. Maz Akhzada, would you like to unmute and ask your question, please?
Sorry, can I ask a question?
Absolutely, go ahead.
About GB 9000, the GPR that you mentioned in previous slide, using for slabs, I'd like to know what data it provides for us.
What data did you mean?
Yeah, what features and what data can, for example, detect the defect in the pavement slab, or something like this?
So normally for slab, if you want to find out slab thickness, you normally look at targets on your grayscale scan. So if you look at this grayscale scan right here, we've found a few targets on the top, so which I'll go through over the next couple of slides and how it works. But essentially, the hyperbolas correspond to each target that you find on your scan. And if you want to look for the slab thickness, instead of having one individual target, you would get a constant reflection from that target. So that would indicate the slab thickness. So in this instance, this target right here at around that 300 mil mark is indicated as a slab thickness.
So I need, for example, the heat map data. What type of data provide us? Can I say that which area is more porous, or which area we have this defect, or which area we don't have?
Look, we might go through the rest of the presentation for a little bit, and then we'll see if we can clarify those questions with some of the slides Joel's got prepared, so we can keep moving forward. But thank you.
Cool.
Thank you.
Yeah. So with the next slide, so this is basically a sort of a way on how it sort of finds out how you get those hyperbolic targets from the targets under the slab. So picture this sort of vehicle as your GPR unit, and then this circular target as a rebar that's kind of pointing outwards towards the screen. So when you have this, when you scan the unit, as you're approaching closer to the target, and around this point, it sends out the radar, and that's when it hits that target, and that's the first point where you'd receive the radar waves back to the unit. And as you approach to the middle of the target, that's where you would get the strongest signal, which would be the middle of the hyperbola. And as you move away, you would start to have this sort of band come off, and eventually it fades out. So at this point is where you would sort of start to receive signal from the target. As you go to the middle, that's where it is strongest. And as you move away, the hyperbola fades away. So for targets that are single points, the middle of the hyperbola will basically pinpoint where your target is. So this is just a small animation, assuming this is a slab, and this is sort of the air interface, so the thickness, the end of the slab. I'm going to play this. That's where it sends its radar, hits the slab, returns. And if you look at the top right of the screen, you would first get a strong signal when it first hits, when it first scans through the slab, and you would get another signal when it finds the bottom of the slab. Cool. And now what happens if we introduce steel, or say a rebar that's pointing outwards? So the first bit, you would still get the top and the bottom, but the moment it starts detecting, well, finding out where the steel is, it starts to bounce off of it, and you would get that first line of that hyperbola. And as you're going closer towards the target, and as you're going towards the middle of it, you would find the peak of the hyperbola. And as you're moving away, you would see that sort of start to fade out, and then you would find the bottom of the slab. So you might notice that there's a little bit of a gap on the bottom. Basically what it means is that with radar, metal reflects 100% of radar when it gets hit. And with other targets, so say non-metallic targets, it doesn't reflect 100%. So basically, if you've got anything that's directly below a metallic target, it won't appear on your radar scan just because the steel is reflecting 100% of the radar. So if you look at here, we can't see the bottom of the slab that's directly underneath the steel because the steel is reflecting 100% of the radar upwards. So one thing to note is that if you're scanning a slab and you've got a very congested orientation of rebar, you might find little gaps when you're scanning for the bottom of the slab just because the metal is reflecting all that energy up. So migrated view. So migrated view is another view of how you could look at your GPR data. So you may recall from the previous slides. Actually, can I go back a slide?
Yeah, this is the bottom button.
Cool, yep. So you may recall from the previous slides that we had that grayscale and we had hyperbolas. It might be a bit too overwhelming to look at to begin with. So with the migrated view, it's a bit easier to sort of find your targets just based on the color coding. But if you look at the later slides, I'll go through over the advantages and disadvantages of using the two views. But basically, with migrated view, what it does is it collapses all the hyperbolas into a single point. So we've got a target here, and we've got our radar, we're scanning. It's starting to pick up the hyperbola. That's our hyperbola, and what it's doing is it's collapsing it all to a single point. There we go.
Play that again, please.
So I'll play that one more time. There we go, that's our target. That's our hyperbola. And now it collapses it to a point. Cool. Right, so these two scans are exactly the same data. It's just that one is in the non-migrated view, one's in the migrated view. So with the non-migrated view, we can see we've got good polarity. We can accurately locate the top of the rebar pretty clearly. And it's also a format that a lot of GPR operators normally use. With the migrated view, it's a little bit easier to understand for new users because this might look a bit overwhelming with just grayscale black and white. Whereas with the color coding, it might be a bit easier just to pinpoint your targets. But if you look at the small blobs, notice how the targets that we place are not directly at the center of the blob. So this is actually one of the disadvantages of just solely relying on the migrated view, just because you won't exactly know where the actual position is. So our recommendation is you actually use both views. So to start off by tagging your targets with the migrated view, and then confirming their depth with the non-migrated view. The next bit so the dielectrics can affect your penetration depth with when it comes to getting an accurate depth when you're scanning. Mainly because if you've got dry concrete, you've got wet concrete, you're more likely going to have a much more accurate scan depth with the dry concrete, because the presence of moisture will affect your radar scan. And of course, moisture can actually change depending if you've got a long outdoor slab at different times of the day. If you have the sun shining, it could affect the dielectric of the concrete. So determining dielectrics. If you look at this table here, the dielectric constant of air is 1, and the dielectric constant of water is 81. So in principle, the higher the dielectric constant, the more wet it is. Typically for dry concrete, we'll have it around 5 to 7, and for wet concrete, it's around 8 to 12. So it's pretty crucial to have the correct dielectric when you're scanning to get your accurate depth. So there are three ways on how you could get the correct dielectric. The first way is just to guess. If you know it's dry, you can plug in any value between 5 and 7. But the two more accurate ways of actually determining your dielectric is by ground truthing and by using a curve fitting function on the ProSec app. So ground truthing, what it essentially is if you know that your slab is 200 mils, or if you know for a fact that the top layer of Rio is 40 mils, you're going to plug in that value through the app by adjusting your dielectric constant to match that value to get your accurate depth. So going over to this slide, we've got two identical scans, the only difference being the dielectric constant. So the scan on the left, our dielectric constant is set at 7, and then on the scan on the right, our dielectric constant is set at 9.7. So one of them is higher than the other one. And if you look at the depth of our target, where our crosshair is, so that's the thickness of the slab, this is around 211 mils, and that's 180 mils. So even if we have a dielectric constant, say around 2.7 off of the actual value, our depth is actually quite different by about 30 mils. Another thing we can do with the ProSec app is when you adjust your dielectric constant, you would get this sort of yellow curve fitting like function where you could try to fit into the hyperbolas to get your depth. So you might start off with a curve that's sort of like very flat, and when you adjust your constant, you can sort of try to fit it in to one of these targets to get your actual depth. So first we would normally place our crosshair onto the target to make sure we're actually matching it with the peak strength, and then we would play around with our dielectric constant to adjust to get a correct constant. So one of the limitations with GPR is that it will struggle to find targets and depth in new concrete. So new concrete basically is fresh concrete, which is moist. So what that means is it's very conductive, and because of that, you won't be able to achieve a good penetration depth, and you won't be able to get a good contrast between your targets and the scan. So in this instance, we could still pick up these targets, but we've got a region where it's quite distorted and we aren't able to see anything. Another limitation, metal. So basically with radar, metal, as I mentioned previously, metal reflects 100% of radar. So what it also means is that if you're scanning on a surface that's steel fiber reinforced concrete, Bondec, you're not going to be able to see anything on your scan. This is what you'll be able to see. Likewise, when you remember from the previous slide, we had the rebars and then we had like some shadowing. That's our rebar targets, and that's our slab. So you notice how...
We've got a question in the chat
Yep.
about how accurate is GPR for measuring the depth of a slab on ground. So the question was, how accurate is GPR for measuring depth of a slab on ground?
That will, in terms of depth, that will depend on the dielectric constant. That will depend on what's in the slab, so how congested the rebar is, presence of any other embedded objects. But in terms of accuracy, it can be around 5 to 10 mils of the actual depth.
Yeah, that's correct. Now, I've actually done a little bit of analysis on the influence. If you've got a ground truth measurement, so you've taken a measurement where the depth has been exposed to bar, or you've exposed the side of the slab and you can measure the depth, and you've used that to set up your dielectric constant, that's when you're closer to that 5 millimeter value. And if you're guessing a dielectric with the hyperbola fitting method, that's more the centimetre or so precision. I just did a little bit of rough maths to work out the error in both of those methods. Actually, Joel and I put a paper together for the Concrete Institute conference coming up. We'll have a little more detail on that in there.
Cool. Thanks, Will. So yeah, back to this image. You can see how the slab is shadowed by the rebar targets on top of it. So if I just go back, yep, that's our slab. Yep. PT, post-tensioning. Post-tensioning is quite distinctive. Reason being is that you know how with rebar, we've got a nice layout, we've got rebar at a good, like, sort of evenly spaced rebar with similar spacing, and they all follow a pattern. With post-tensioning, it doesn't follow a pattern. You could find it very close to columns or beams, and also you could find them slag, or you can find several of them in one area bunched up. So usually when you want to scan for PT in general, you would have to take long line scans just to understand what's under the slab, and then find these statistical outliers. So this one is, and usually also one thing, sorry, the PT is also quite close to the bottom of the slab as well. Just like in this instance, we've got a target that's just right on that slab. And then the things to consider when you're actually going out to do your scanning, it's not as simple as just bringing your unit and then bringing it out to site and just getting started right away. There are a couple of things that you need to consider. So take a good read at this slide, but basically there are a couple of questions you need to ask or you need to answer before you go on site. Is the surface smooth or rough? Do I have enough room? You might find out with the larger units, you might not have enough room if you need to scan in tight or confined areas. Where's the required target in relation to the accessible surface? What are you actually looking to scan? Were you looking to scan just for rebars, or were you looking to scan for anything that's on site that you need to know before you cut or drill? Or are you only looking to scan just for PT? And then even you have questions in regards to the geometry. How thick is the slab? Do you have any idea on what the real layout is? And also, yeah, what targets are most important? Also on the reporting side of things, do you need to write a report? What sort of deliverables do you need to present to your client? Are photos just enough of marked spots on the ground, or do you need a full visualization of your scan into reports with targets and markups to show it to a customer? So there's a lot of things that you need to consider, because if you don't say, if you've got a client that actually needs a full data visualization, photos of where you've marked on the ground won't do enough, which means you would have to come back on site again, scan it, make sure your data is what the client needs. So this is a small animation on how you would normally scan if you just were to mark and locate. The main thing is, first you just need to pick a point, mark that point, and then you would do preliminary scans, so maybe scan around it just to get a good general feel of where the reel is. And then yeah, you would scan in either sides of the point. Just see if I can play this one. Yep. So they first performed 3 line scans, one to the left side, one right in the middle of the point, and one on the right. And the red points basically denote where the rebar is. Just play the next slide. Just give me a moment. Yep, should be able to play the next one. Yep. So we performed another 3 scans. We found rebar here, there, up there, and here right in the middle. So the point we've picked pretty much has a rebar just right on top of it. So we know not to drill this. If you were to drill, you wouldn't drill this point because you'll be just hitting the rebar. Yep, and that's when you would move the point to right. You would move the point there. And now this is another example, but before going to it, once you've moved your point, you would want to just take another couple more scans just to make sure there's nothing there. And here's another example. So they've done a scan down here and a scan down here, but it does not necessarily mean that there's a rebar that's actually going this way and going this way. You could have an orientation where this is like a standalone rebar. We've got another lone rebar up here, and we've got one just going through. So just doing 2 scans isn't really enough to paint the whole picture. So really it just looks like there's rebars going there, but it's actually not the case. So if you were to take another scan around where you've picked your point, this is how it would look like. You'd get a target here, and that's when you would figure out how the orientation of the rebar is. And then you would obviously want to just make sure. Yeah.
You'll find that with this kind of orientation, sometimes the grid scan functionality in the radars is going to be a useful tool, because then you're taking 6 or 7 scans in one direction each way, making it much easier to get those misaligned bars. I know I chatted to some of you before you started the session about what do we do if we don't know the way the bars are aligned. The grid scan's a good tool for that as well.
Yep. So in the other example, we've scanned and we've got 3 pieces of reel. We've got another 3 down there. And then we've got 3 here right in the middle. So it looks like we could move a point somewhere right, in between all these pieces, right? Looks like it's going this way. So it looks like there's another reel here. There's another one down here. Sorry, down here. There's one up here. So it looks like it's pretty obvious we can move this here or here, so we're not hitting any reel. But that's not the full picture. Keep playing. So what you may notice is that you could also have something just pointing out of your normal orientation. So if you were to just end it there, you would still end up hitting this reel. So the way to sort of mitigate through this is that you would still want to scan where you've picked your point directly on top, just to be sure, and see you've found the pieces of reel, and then you would move it up somewhere else. So the real reality is nothing is really perfect when you go on site. Nothing's perfectly like a grid. There's always going to be orientations where rebar would just be patterned differently to what you can think of. So it's always good to just take as many scans as you can. So just in short, just coming off of Huw's slide, with GPR, you can find the spacing between 2 rebars. You can also find the exact location when you scan. It's good for finding depth. You can find post-tensioning. You can also scan for the thickness of the slab. And you can also find hidden features, find footings, dial positions, and defects. But what GPR can't do is it can't be able to find the size of the rebar. It cannot determine the grade of the rebar. And it also won't be able to find concrete strength, which you would use a Schmidt hammer for it.
Okay.
Yep, that's all for me for now.
So before we finish up, I've got a question saved in the chat I'll come back to in a second. But I just wanted to check in with our in-person attendees. Does anyone have any questions or, beg your pardon, information we didn't cover? Yes.
So on one of the slides, you mentioned, smooth versus rough surfaces.
Yeah.
What sort of considerations would we need to, have in mind with smooth and rough surfaces?
I think with that, it's mainly because if you've got a smooth surface, the unit can flow like normally. But if you've got a rough surface, you've got bumps. You might have a surface where you might find that the wheels of the unit might not, you'll find it very bumpy. So you'd find your your scan and your targets will just be a little bit off by a few mil. Yeah. So that's just something to consider. And obviously, if you've got concrete dust or other fragments or anything, you'd want to just sweep it off before you scan.
Okay. And would that, throw off the little antennas if it's like a real bumpy surface, or?
I wouldn't say we'd throw it off. It would just make your scanning less smooth. Okay. But if you've got a very big, say something as big as like a pothole, then
Yeah.
you know you wouldn't want to scan on
Okay.
it
Yeah.
and damage the radar.
Okay. And something else you mentioned was coatings.
Yeah.
But you know, would something like a zinc-rich paint mess with it, or you know, what kind of things do we have to take into mind for coatings?
No, normally not.
Okay. Yeah. So it's just an actual like piece of metal.
Yeah, so
Yeah,
you've
that
got
would-
like steel fiber reinforced. Yeah,
Yeah.
definitely.
Okay.
Like if you stick like in like a specific metallic reflective tape, that's
Yeah.
going to come up on your scan.
Okay.
Yeah.
Yeah.
So we do have a question from the chat. Do PCTE recommend GPR operatives for projects, or do we do the work? Now, PCTE are suppliers, so we're always happy to put you in touch with some of our customers who are able to help you out, but we won't come and do any scanning work for you, or do any wet hire type operations. Do we have any other questions from the wider room? Yes, if you could put that across there.
Yeah. I was just wondering if you're using, say, one of the biggest scanners like the GS 9000, and say you're doing like a really big area like a bridge, or a car park, that sort of thing, and you want to sort of relay the information to the client or whoever, because it's such a big area, you can't really like spray paint like the whole bridge deck or something like that. How would you give that information to the client or whoever you're scanning for?
So with the GS 9000, it has, so you've got your main swamp of data, so you can do a large line scan, and it also has a mode where it's called a free path mode, where you'd have a satellite image and you'd have your scan portrayed on that satellite image.
Yeah, okay.
So one way of delivering that info to your client is if you're actually scanning outdoor where there's no obstructions, you've only got the sky on top, then you can provide that satellite image with the scan overlay view to your customer. But if you're in an indoor car park and scanning, you've got that large, so as long as you know where your start points and your end points are on the ground, you should be fine, because with that large unit, with the high frequency antenna, it has 35 channels with a spacing of 2.5 centimeters. So you're effectively collecting a lot of scans in just one pass.
Yeah,
so you'll
okay.
be able to see if, say, the Rio is, like you'll see the Rio position, you'll also see it sort of slightly change in orientation.
Yeah, okay. But so would you would you give them an iPad or something to navigate that aerial shot that you're talking about? Or like,
So, practically with the GS 9000,
yeah,
it doesn't necessarily get used for locate and mark projects, though you absolutely could. It'd be a
Yep.
great tool for it.
Yeah.
The kind of projects it gets deployed for are going to be very specifically where that large-scale visualization is involved,
Yep.
but also where geolocation is involved. So a large part of the establishment of that work and the post-processing you do for that work is to achieve a survey accuracy of maybe a couple of centimeters precision,
Yep.
and then overlay that information to the client's information system. We've done a bit of a example I'll show you when we take a break,
Yep.
where we've lined up a point cloud scan of our car park with survey data from the GS 9000.
Yep.
So that can be used to sort of show the reinforcing under the ground in a point cloud of the reinforcing and a point cloud of the car park.
Yeah, okay, that
So
makes sense. Yeah,
basically,
thank you.
the way we put large information in context is we survey. We know where it is
Yep.
in the world, not just on the iPad.
Yeah, cool. Gotcha. Yeah, thank you. I also had another question.
Please.
Going back to the question about scanning different surfaces and stuff like that, if you did have like a sort of like a non-conventional surface, one that wasn't flat, I don't know, say it could be like an RC pool, like the corner where it's curved, or maybe you have like an exposed footing that's been like, totally scabbled away, just something that's like completely not flat. How would you go about like finding the rebar for an element like that? Would you use this sort of scanner? Would you use the smaller handheld one, or would you just have to maybe source a totally different instrument?
So with curved surfaces, so like columns, you could use the smaller one.
Yep.
So we found the small one can go around it pretty well. With this unit, the encoder wheel is the rear right wheel, if I'm correct, Will. But
Those will all operate together, Joel. So
yeah, and they operate together. So as long as you have one of the wheels just sort of going over the point, the unit should be able to collect that scan.
Yeah. Okay. Yeah. Cool. Because there was one specific case where there was a job site and the like they had like an exposed footing and it was
Yeah.
like a very rugged, uneven footing that they wanted to
Scan on top of it.
Yeah, they wanted to know where the rebar was because they wanted to get chop that footing off basically.
Yeah.
And so they wanted to scan it. But I was thinking like how would they be able to scan it if it's not flat? You know what I mean? And if I can understand a circular column that could be quite easy with a handheld scanner. You can sort of go round the column, but if you've got a surface like that where it's almost like a Mars rover or something going over it, would you still use like one of those, or could you be able to like put like a flat surface, like a fabricated say flat surface, would that still like say made of a different material, could that still then just use the GPR to penetrate down and find the rebar or something like that?
So one of the things with GPR that it will do is we're detecting the 0 point from where that radar energy reaches the surface of the structure.
Yep.
So it's actually quite practical if you've just got like an exposed aggregate finish, put a core fluid down, put something plastic, not particularly influencing the radar.
Yeah, okay.
And slide it over that smoother surface.
Yeah.
That's a good troubleshooter. It won't get you out of every case, but in many cases, it's a good way to do things.
Yeah, awesome. So maybe like plastic, were you saying, or like perspex,
plastic
something
or something like that. Yeah.
Yeah, okay.
I say core fluid because you just nick them from the politicians.
And that won't have too much of an interference with the
it's
dielectric.
going through a piece of plastic already to get out of the antenna.
Yeah, right.
In an air gap, and then
Yeah.
reflecting from that concrete, and that's how we set the 0 point.
Yeah,
so
cool.
yes, you need to be a little careful, maybe what's the precision of your depths and stuff.
Yeah.
But it's a good troubleshooter.
So like on the radiogram, you might potentially see a bit of air layer first or something, then the concrete, then the
It would be
rebar?
more likely that you get stronger horizontal banding. With a bigger air gap, it's still going to start at 0. But what happens is with that bigger air gap, we lose more energy. So when we have to put the gain higher, so the reflection of the air looks stronger. It's something that you sort of learn by doing.
Yep.
But basically, if we've got a scan that's with a bit of an air gap, it will come out on top that way. Now, if I can, I do have one question from the chat, which is how accurate is GS9000 in space in large-scale works like for pavement thickness evaluation? What do you mean by accurate in that particular context? Are we talking in terms of the depth precision? Because you need to calibrate like you do a dielectric with anything else. We do have in the Insight software some thickness detection coming in for exactly that pavement thickness evaluation kind of job. But to give you an exact number, it's more something that you'd actually establish as part of your procedure. Because if you have the large data set, and then that would give you some information once you analyse it on how accurate it is, plus you'd have the performance and the dielectric considerations as well. The bigger the project, the more it becomes almost a process to work out the error in your survey, which is something surveyors would be more familiar with than maybe an engineer would. Another question was actually location and the location accuracy in plan view should be, again, we sort of, with the GNSS using the correction, we're within a couple of centimetres of lateral position, and again, the depth is more dependent upon the setup of your radar. We've had a question about using the GS9000 for asphalt pavement. Absolutely. Its range of depth in the high frequency antenna that was discussed will absolutely be appropriate for that job. You've also got, if you're actually doing location work, there's a separate lower frequency antenna package that's more appropriate for deep location, pipe location tools like that. Now I am going to come back on your previous question, Maz. I hope I'm not being too informal with the name. I do apologise if I am. Regarding the GP8000 and GP9000 equipment, what type of data and feature can the heat map provide us if you use it for a pavement slab? Can it detect defects in the concrete slab, and can it show more porous areas as a heat map? So the heat mapping, which we look at from the basic 3D processing, is mainly to show the reinforcing location. Yes, it's based on the signal strength, but it's not controlled for gains. It's not perfect, but if we get into GPR insights and we start to, rather than evaluate, say, the intensity of the reflection directly, visually. There is deterioration mapping processes, which compare the average signal strength over an area, and that can begin to tell you a little bit about if your concrete has regions which it's a bit less permeable, which might be moisture, might be voiding, might be damage. So that's based on the American standard. Sorry about that, I'll bump the sound up on the mic a little. Yes. Is that better?
You can go first.
So say if you have any like underground or sort of buried structures that are metallic, like water services
Stand
and
up
things
if you
like
could,
that.
please.
Yep.
Yeah.
I'll stand up.
Oh, stand. All right.
Yeah.
So-
Yeah. So say if you have any like buried metallic structures, would your radar be able to like scan those, or
Yeah,
would it come up as a feature? Or
It will come up as a target for sure if
Yeah.
it's metallic. So it will definitely come up as like how we got rebar as targets as hyperbolas. You'd get the same targets as well.
just much
It'll just
wider.
it'll just be deeper in your scan.
Yeah.
Depending on how deep you intend to
It's
scan.
mainly going to be a matter of depth penetration. So the typical concrete scanners, half a metre, a little bit more,
Yeah.
Yeah.
is expected performance. So
Yeah.
if you wanted to do something like buried subsurface structures,
Yeah.
you'd actually go to the larger
The push
utility
cart
location
radars.
antennas, and that would be more appropriate for that job.
Yeah.
But it's done quite commonly.
yeah, and say if you've got like I know some buildings that use like polymer or like plastic sort of pipeline or pipes
Hmm.
and things, would they come up as like a lacquer feature, or would there be like any sort of
So
thing?
polymer and plastic is not going to be a lacquer feature.
Yeah.
It's going to be an open void inside.
Yeah.
So what you get is a weaker reflection.
A weaker
Yeah.
reflection. Yeah.
Okay, yeah, that's all from me.
Hi, actually, in case of a slab which is resting on the ground, if
Yeah.
there is a crack or void just underneath the reinforcement or linear crack, can we use this GPR scan for that case?
For cracks, no. You'd probably use other tools, which will actually cover up in the rest of the day. But for voids, it depends on how big the void is. If it's a big, large air void, it could be able to be picked up by the GPR. But if it's very small, you may not get good contrast in your scan.
If the void is linear and it can be just underneath the rebar, because the GPR just reflect all the
Metallic, yeah.
matter from the...
Yeah, if it's directly underneath the rebar, it won't be able to find, because remember the metal shadows it shadows anything that's underneath it.
Okay, thank you.
Is that something like ultrasonics probably better for? Or?
So the question was, would ultrasonics be better for that? The answer to that is absolutely. So if you, in the last session for today, I'll be going into detail on ultrasonics. We can discuss a little bit about voiding under rebar. It's not easy,
Yeah.
but we can get some
Yeah.
sensitivity with ultrasonics. You're not going to get anything really appropriate with radar.
With radar.
It's not like a lot of these things. It's not that a good operator with really favourable conditions can't do some void detection. It's that favourable has to be giant chunks of nothing. It can't be distributed voiding or honeycombing and stuff like that. Except maybe if you're going into where you've got the big antennas taking a lot of data, we can start to take advantage of statistics to look at significant drops in signal and such, but you can't do that with a handheld scanner.
Okay, thank you.
And I guess maybe a dumb question, but it doesn't have to be concrete, right? It can be, I guess, anything that the radar will kind of
Yeah.
just bounce through.
Exactly,
So yeah, I mean, I guess like going back to what Neil was asking about buried stuff. If you just had a chunk of soil or whatever, you could still pick up stuff.
Yeah,
under that.
definitely. So
Yeah.
that's where we'll use the pushcart radars. They're mainly used in
Okay.
soil, even just like the median strip down.
Yeah.
Still be able to find it.
And I guess how does that play into the whole dielectrics thing? If you've got mixed materials, say you got a bit of carpet, you got a bit of concrete,
Yeah. So with
do you
like
average it out or?
So with for instance, if you're scanning out with soil and you got the different layers, so with the GS 8000 and 9000 using the low frequency antenna, you're actually able to adjust a different dielectric for a different different region of that, for instance. You can't do that with the handheld radars because they're specifically used for concrete. But with the pushcart radars, you can definitely adjust it with to a specific region.
Okay, yeah, thank you.
Yeah.
Do we have any remaining questions?
Yeah. No. One.
Yep. One at the back. If you
yeah.
just be, so if you can be visible. That's about right. Cool. Thank you.
For corrosion, can GPR pick up any corrosion of bars? If so, how well can it? Or
We're back to that deterioration issue. You're not doing it with a handheld scanner, and you'd want to have like incredibly bad expansive corrosion to sort of break the concrete.
Yep.
Or very heavy leaching of like chemicals and water and stuff
Yep.
around it to pick it up statistically. It's not your right tool. We're doing corrosion with Ruben in 2 sessions from now, so that's the
Yep.
second last session of the day. So we'll talk corrosion. Radar doesn't have a big role to play in corrosion,
Yep.
except maybe a bit of cover depth analysis where it's a useful tool.
I was going to say, like, because if the diameter, I know I can't tell rebar size, but if the diameter of the bar was like significantly increasing with
See,
corrosion.
actually, that still doesn't work because the
Yep.
hyperbola shapes, provided it's round,
Yep.
it would need to be gigantic to change the size of the hyperbola.
Yep.
Like going from even from like a 30 mil bar to a 15 mil
right.
bar, that's still the same hyperbola.
Gotcha.
It might
Yep.
look a bit weaker, but it's not going to change in a way you could detect by observing visually.
Yeah.
When we talk hyperbolas bigger on things like post-tension ducts,
Yep.
we don't mean because it's a wider circular element. We typically mean because it's like a flat element, so it comes up to the
Yeah.
flat, then goes over the top and goes down.
Right.
Or maybe it just looks stronger because there's more metal. Please, again, I know that I spend a lot of time in cover meters talking about diameter being a bit rough. Diameter is also a bit rough on radar.
Yep.
This is unfortunately why we do need to go and investigate with corrosion investigation. We can do we can sort of look at the rate of corrosion, how likely things are to be corroding, but our investigation is more structural. It's more about if we're actually getting insight. Okay, we've got another question from the chat. Do you see issues with scanning through 20mm thick render into a rough slab for readings? Or what would you recommend for this? The target on this project was Rio pattern and spacings only. Doesn't sound like it would be a huge problem. If it's not like metal reinforced, that it's just a solid block of a different material, the main effect would be maybe some subtle differences in dielectric, so your depths would be a bit rough, but spacing and reinforcing pattern seems to make sense, though it's one of those behaviours where you'll, like a lot of NDT, you'd go and do the job and you'd see what you get, but I'd be pretty confident giving it a try. Is the curve fitting only available with a pro subscription? No, I don't believe it is anymore. I think all of the lights have it enabled as well, Joel. Is that right?
Yeah, I think it was a recent update, I think a couple of months ago, where the lights now also have the ability to do that curve fitting. Actually.
Yeah, so your curve fitting is available on both.
Right, so
double
if-
check question from the room.
Yeah, final one. So say if you have like an active ICCP system
Mhm.
in like your floor scan area, like they have like usually like ribbon anodes or
Yep.
like a mesh or something. How would you, is the scanner sophisticated enough to differentiate between like?
It won't differentiate. They're both just a chunk of metal.
Yeah.
be
They'll both
found
come
like a
up as
chunk of metal.
targets.
Yeah. Okay.
Yeah.
All right. No worries. That's all.
Okay. I think that might be it, unless we've got any final questions on the chat. It's been it's been a really good session. Thank you very much for getting so involved, getting so active during this. We're going to take a lunch break. So we'll be back at 1 o'clock for the next session, which is going to be on the correct use of Schmidt hammers. Thank you so much.